Hi, everyone. So on hyperbolas, on my Math 141 final, I mostly wanted people to remember x squared minus y squared equals 1 opens along the x-axis. Notice there's an x squared in front here, whereas y squared minus x squared equals 1 opens along the y-axis. Notice the y squared is in front here. Again, flashing, here's x squared minus y squared equals 1, horizontal, opens along the x-axis. Here's y squared minus x squared equals 1. In purple, opens along the y-axis, vertical. I'm now going to look at more general notes on hyperbolas. This is optional beyond this stuff over here. All right, remember that hyperbolas have two branches, and you get a hyperbola when a plane intersects a cone in the two branches. All right, and it does not go through the center. If you go through the center, you get a degenerate hyperbola, the intersecting lines. But in general, you would have two branches that go like that, a hyperbola. Again, here are some examples here. Also, y equals 1 over x, where the coordinate axes were the asymptotes. We talked about the geometric locus definition, which told us why we use hyperbolas so that tracking stations can figure out where an explosion may have taken place. If this tracking station heard an explosion, say 5 milliseconds before this tracking station. Also, remember when Malaysian Air lost some airplanes? You might have wondered, why was it that in the news you saw these big hyperbolic branches? Oh, we think the plane may have crashed somewhere along this branch. like this very wide branch over here. Okay, well, it's because of these principles. All right, some terminology here. So the center of the hyperbola, unlike an ellipse, which kind of eats its center, all right, hyperbola does not eat its center. The center is in the midpoint. It's in the middle between the two vertices over here, the two sort of turning points for the hyperbola. Right. The foci are actually further away from the center than the vertices are. So this thing really is turned inside out from an ellipse. Okay, remember, for an ellipse, the foci were closer to the center than the vertices were. All right. So A, the distance between the center and each vertex, same as for an ellipse. C is the distance between the center and each focus, same as for an ellipse. But now, for an ellipse, C was less than A for an ellipse. For hyperbola, C is greater than A. Okay. And later on, this will mean, by the way, that the eccentricity will be greater than 1. Okay. It's between 0 and 1 for an ellipse. Now, normally when we draw hyperbola, think Scrooge, bah humbug. First you draw a box, then you draw the asymptotes for the hyperbola, then you draw the actual hyperbola, the two branches. Bah humbug. Now, how do you draw the box? Well, first you find out where the center is, all right? And we need to know what A and B are. A, again, is the distance between the center and either vertex. And of course, the vertex is actually on the hyperbola. The two vertices are on the hyperbolic branches, over here and over here. B is the distance between the center and these points on the box. These points help you draw the box. They're not on the hyperbola. So you want to draw the box with that as the center of the hyperbola, and that passes through these 4 points like so. These points are the midpoints of the 4 sides. Okay, a box, it can be a rectangle or a square. And the asymptotes are drawn as dashed lines through the diagonals of the box. C, again, is the distance between the center and each focus. All right. Instead of a major axis, we have a transverse axis, 2A, connecting the vertices. The conjugate axis is 2B. And by the way, there's no guarantee that A is greater than B, as it was for an ellipse. All right. Now look at this. What's the relationship between C and A? Notice that C is bigger than A. The foci are further from the center than the vertices are. C is greater than A. Look at this equation, this formula. C squared equals A squared plus B squared. It looks more like our classic Pythagorean theorem. Remember, we had a minus sign here for ellipses. Okay. If the center is at 0, 0, Here's standard form for the equation of a hyperbola that opens along the x-axis. It's horizontal, and the center is at the origin. X squared over a squared minus y squared over b squared equals 1. Remember, for an ellipse, we had a plus sign there. And bear in mind, a squared is always the denominator on the left. It doesn't matter who's bigger, who's smaller. A squared always corresponds to the denominator on the left, assuming that the signs are appropriate. Positive, negative, positive. Right. For y squared over a squared minus x squared over b squared equals 1. A squared is on the left. This time the y squared term is on the left. We have a vertical ellipse. So for determining whether the hyperbola is horizontal or vertical, you're looking at whether the x squared term or the y squared term is on the left, assuming that the signs are correct here. Positive, negative, positive. All right. We have equations for asymptotes. The key idea is the slope is rise over run, right? The slope is rise over run, and these are going to go through the origin. If the center is h comma k, we translate. We substitute x with x minus h. We substitute y with y minus k. Okay, it gets a little confusing here because in number 2, you substitute y with y minus k, the second number, the second coordinate. Right, that translates. And the asymptotes are translated in a similar fashion. Eccentricity, E is c over a like before for an ellipse. This time c is greater than a. It's kind of top heavy. E is greater than 1. So for example, here, the eccentricity is 2 for this for this hyperbola. The eccentricity is 10 for this hyperbola. They look like parallel lines. All right. So let's say that you're given an ugly equation for hyperbola. A hint is that the y squared and x squared terms are on the same side, but have different signs for coefficients. We can group terms, group the y stuff and the x stuff. I would recommend putting a plus sign in the middle, though, because if you put a minus sign, you're in danger of messing up signs here. So separate with a plus sign. That's safer. All right. Non-zero constant on the right. Complete the square. Compensate as appropriate. Balance the equation as appropriate. We now have PSTs over here and over here. Factor them. Right. Divide by the right side. So we get a 1 on the right side. All right. That's in standard form. The y square stuff is on the left, so it's going to be a vertical ellipse. Opening up and down. The center makes the left side 0. Be careful, x equals negative 2 over here. Y equals positive 6 over here. Be careful of the order. All right. A squared is on the left. A squared is 4, so A is 2. B squared is 1, the right denominator, so B is 1. A is 2, B is 1. C squared is A squared plus B squared. We get that C equals root 5. We've talked about asymptotes. You can get their equations. To graph the hyperbola, here's the center. Right. Draw the box. A equals 2. It's a vertical hyperbola, so you go up for this vertex, go down for this vertex. A equals 2, B equals 1. That gets you over here and over here. You get these points here. Together, the vertices and these two other points help you draw the box. You draw the asymptotes through the diagonals of the box. It's a vertical hyperbola. The vertices we found, they're like the turning point, sort of. You can also find the foci. You also go up and down for the foci from the center for a vertical hyperbola. This time the foci are further from the center than the vertices are. So that's how you would graph a hyperbola. All right, and we talked about applications. Again, this was all optional, but it all makes sense. Next time, polar coordinates and polar curves.